In this unit of study on Newton's laws, we're very concerned with the concept of force. So to be clear, let's define what a force is. It's pretty simple. A force is simply put any push or pull. Now, what units do we use to measure force? Newtons, or simply N for Newton. Pounds is one way of measuring force, but we're going to stick to the metric system and try to refer to measurements strictly in units of newtons. Now, a newton is the same thing to a kilogram meter per second squared. But that's a mouthful to say all that, so in honor of Isaac Newton, we refer to that in his name. So this begs the question, how many different ways can you push or pull an object? Anybody who's played with magnets understand that they can attract one another, and or they can repel one another. They can push or they can pull. There's a bit of action at a distance that takes place. They don't necessarily have to make contact with each other to be able to exert that force. There was a time, less than a couple centuries ago, that it was believed that magnetism was a separate force independent of electrostatics. So you may have seen demonstrations where a charged wand can influence the behavior of a couple little metal foil leaves inside of a glass jar. So the two repel each other if they share the same charge. Likewise, if a student puts her hands on a Van de Graaff generator and electric charge conducts through her body and into every fiber of her hair, then each fiber of hair, having like charge, wants to repel one another. Turns out electricity and magnetism are not separate types of force. They're really both one type of fundamental force that we call electromagnetism. All magnetic forces, in essence, are due to the interaction of charged particles in motion. And all electric forces, or electrostatic forces, are due to charged particles at rest. But because velocity is a relative quantity, if you're standing on board a train and you look at objects on a table next to you, you might say that they're at rest. You don't feel the motion of the train down the level tracks. A person standing here, if they could look into that train, would say that this object is in motion. So yeah, motion and velocity is very much a relative quantity. Albert might say the motion of the object on the desk is something very different than what Betsy would say about it. So if electrostatic forces are due to charges at rest and magnetic forces are due to charges in motion, but motion is relative, then it might make sense that these two forces are really manifestations of the same thing. So there's one of the four fundamental ways in which things can be pushed or pulled in our universe. That it can be due to the force of electromagnetism. Of course, gravity is another force we're familiar with. The same force that causes apples to fall from trees is the very same force that causes the moon and the earth to be attracted to one another. The fact that those are both examples of the same force was not obvious back in Newton's day in the 1600s. To us, it might seem intuitive that those are equivalent phenomenon. We'll learn eventually that the force of gravity can be calculated if you know the mass of one object. So we'll say mass number one is the moon, and the mass of a second object, mass number two, is the earth. And then you know the distance between the two of them, measured from center to center. We can call it D, we can call it R, we can give it any symbol we want. And by the way, the distance between the Earth and the Moon has been exaggerated in this picture. It's much smaller in this picture than it really is. The distance between the Earth and the Moon is about 60 times the radius of the Earth. In other words, you could put 30 Earths end to end to end to end before you ultimately get to the Moon. Anyway, we'll find that if we know those quantities, the distance that separates the two objects and the mass of the two objects, then we can find out how strong the force of attraction happens to be. We say that force of gravity is equal to, we take the product, we multiply the mass of the one object times the mass of the other one, and then we divide it by the distance between the two of them squared. Of course, dimensionally, those units wouldn't work out. That would be kilograms times kilograms over square meters, and that's not a Newton. So there's a constant of proportionality that goes into this equation. Turns out it's a very small number, so we give it the symbol capital G, not to be confused with lowercase g that represents acceleration due to gravity on Earth. Here we're talking about a much different universal constant. Happens to be equal to 6.67 times 10 to the negative 11th, right? So 0.0000, eventually I'm going to say 667. And the units for that are newtons multiplied by square meters divided by square kilograms. I'm getting a little bit ahead of myself with this one. I think for our first several units of study, we'll find a shortcut to this. We'll say because we're studying objects that are always on Earth, perhaps we're not always interested in the moon's attraction to the Earth, but we are interested in the apple's attraction to the Earth. So if mass number 2 is always the Earth, and by the way, if I exaggerate the picture of this tree and the falling apple, for all practical purposes, the distance between the apple and the center of the Earth is nothing more than the radius of the Earth. The distance between you and the center of the Earth is the radius of the Earth. So if we know the mass of one object is the Earth, the distance between two objects is the radius of the Earth, and this capital G is always a constant, then we could just calculate all of the circled parts of the equation and then leave the mass of the first object free to be anything. It could be an apple, it could be the moon, it could be a person, you name it. So we'll just call it M, and then we'll figure out what the rest of this is. Well, it's no coincidence. Actually, all the rest of this stuff is that lowercase g of 9.8 meters per second squared. So we have a shortcut for calculating the force of gravity. We just say it's the mass of any one object that's in the presence of the Earth multiplied by the acceleration due to gravity caused by the Earth. And that's another one of the 4 fundamental forces in our universe, another way that things can be pulled. There are only 2 more other fundamental ways in which objects can exert forces on one another. Now let's go back to this electromagnetism. What we know about charges at rest is like charges would repel. So all these protons here in blue have positive charge. And these 2 protons, based on the electrostatic repulsion, should repel each other. However, a nucleus exists without flying apart. So there must be some other force that allows protons to exist in the presence of other protons within the nucleus of an atom. And you can't argue it's because the neutrons are pulling them in, because the neutrons don't carry any charge at all. And it certainly would make sense to say that the electrons that are orbiting around the nucleus do anything to keep the protons together. If anything, they would only want to attract those protons and make the nucleus want to fly apart that much more. So the reason that nucleus can hold together without all the protons repelling each other and flying apart is due to another one of the 4 fundamental forces known as the strong nuclear force. And it basically is a force that really doesn't exist over long ranges. Gravity exists over very large ranges, right? 60 times the radius of the Earth is pretty far. And this action at a distance that you might have felt before when magnets are kind of close to each other, once the magnets get farther away, that force diminishes really quickly, right? With gravity, the distances can be tremendously large, right? Far greater than just the distance between the Earth and the Moon. The Earth is bound to the Sun, and that distance is well, I don't need to tell you, right? So over these astronomical distances, the force of gravity still dominates. But the strong nuclear force isn't like that. The strong nuclear force rapidly diminishes at distances greater than the diameter of a nucleus. So we're not used to seeing protons attracting other protons because we can't witness things, we can't see with our own eyes at ranges that are that small. Okay, and then lastly, there's something known as the weak nuclear force, or sometimes called the weak interaction. And that's a force that extends over even smaller ranges than the strong nuclear force. It's a force that doesn't extend really beyond the diameter of a single nucleon. And a way in which it reveals itself is in some nuclear decay processes. The weak interaction is a force that can cause a neutron to decay into a proton along with some other fundamental particles. This is actually an example of what's known as a beta decay process, where the nucleus is shedding an electron. We won't deal with the weak or strong interaction in this course really any more beyond this lecture. Our emphasis will be on gravity when we talk about force, and almost all the forces that we encounter are actually electromagnetic in nature. And that includes the tension in a rope is really a manifestation of the electromagnetic fundamental force. Friction is also a form of the electromagnetic force. Adhesion. What else? Well, just about any force you can think of that you encounter in your daily life other than gravity, right? If you see something fall down, of course, gravity is the reason it got pulled. But any other force you encounter is in some way an example of the electromagnetic force.